Today, let's solve a very interesting equation. N factorial is equal to n terminal. So a few days ago, I made this video where I discussed the question mark operation, and that is called a terminal, which is just an addition version of the factorial. Here's an example. If you have 6 factorial, you will just do 6 times 5 times 4 times 3 times 2 times 1, which is 720. But if you have 6 with a question mark right here, which is called terminal, you'll be adding this up instead. So 6 plus 5 plus 4 plus 3 plus 2 plus 1, and that will be 21. And this is also called a triangular number. Okay, how do we approach this though? Firstly, n factorial, we can use the usual definition. When n is a positive whole number, that's just n times n minus 1 times n minus 2, and so on. We stop when we reach 1. And n terminal is just n plus n minus 1, and so on, and we stop when we reach 1. Okay, here's a fact. On the right hand side here, we actually have a very nice formula because this is just an arithmetic series. You do the first term, which is n, and you just add the first and also the last term, which is n plus 1, and then divided by 2. So this is equal to that. That's fine. And on the left hand side, we still have this. Okay, since n is not equal to 0, you can cancel out the n both sides. But how do we even continue right here? Because I don't even know how many terms I'm supposed to have right here, right? So this is how we are actually going to do this one right here. We are actually going to just be plugging some numbers and see which numbers work. And then after some point, you will see that factorial is actually going to be growing much faster than terminal. And then we'll do a mathematical induction proof so that we can make sure we don't have any other solutions. So here's the deal. N equals 1 works because 1 factorial is equal to 1 terminal because 1 is equal to 1. Done. And if you look at when n is equal to 2, 2 factorial versus 2 terminal. Well, this right here is 2 times 1 versus 2 plus 1. Of course, 2 is not equal to 3, so this does not work. And if you check when n is equal to 3, 3 factorial versus 3 terminal. Here, we have 3 times 2 times 1 versus 3 plus 2 plus 1. This right here happens to be 6. Likewise, this right here happens to be 6. So for this one, it does work. So this right here is also a solution. Okay, how about when n is equal to 4? You will see that 4 factorial versus 4 terminal. This is 4 times 3 times 2 times 1, which is 24. But this right here is 4 plus 3 plus 2 plus 1, which is only 10. So does not work. And in fact, you are going to see that as long as n is greater than or equal to 4, factorial will be bigger than terminal. So we will for sure not be able to get any other solutions besides 1 and 3. Now, let's see the proof. So here I'm going to claim that n factorial is greater than n terminal for positive whole numbers greater than or equal to 4. I'm just going to write yes. N equals 4, 5, 6, and so on. Now, let's go ahead and do the proof. PF. And of course, this right here, we are trying to prove a statement involving positive whole numbers. So we'll be using mathematical induction. First, I'm going to check the base case. And of course, that's just when n is equal to 4. So if I plug in 4 into here and here, we get 4 factorial, and it's not greater than 4 terminal. Yes, we saw that earlier. This right here is equal to 24, and this right here is equal to 10. So of course, this is correct. Done. Now, inductive hypothesis. I'll just put down IH. So right here, we are going to assume that this right here is true for some number k. So I'll just write k factorial is greater than k terminal. But remember, we do have this condition here, n is equal to 4, 5, 6, and so on. And we saw that when n is equal to 4, this right here works. So we can say this right here is true for some k greater than 4. And this is going to be crucial later on. Okay, once we have the assumption, what are we trying to do? Remember, once we have the inductive hypothesis, our goal is to show that this right here is also true for k plus 1. So it's going to look like k plus 1 factorial. We need to somehow show that this is greater than k plus 1 terminal. So keep that in mind. Therefore, I'm just going to say, let's go ahead and check k plus 1 factorial. And then we had to do some algebra, and somehow we can make it greater than this thing right here. Okay, let's just go ahead and just simplify the factorial a little bit. This right here means we start with the inside, which is k plus 1, and we multiply by the next number, which is just k, and then k minus 1, and so on, so on, so on, until we reach 1. But all that's really just k factorial. So it's just like this. But notice, we have this k factorial here, and by our assumption here, we can say this is greater than k terminal, which is quite nice. And bring this down. And everything's positive, so the inequality works nicely. Good. Now, how can we continue though? Well, remember the formula for the terminal? This right here is just going to be equal to the inside times the inside plus 1, and then divided by 2. Right, the formula I mentioned earlier. And now let's bring this down again. Okay, so far so good. Let's take a look at what we are trying to achieve. Let's use the formula right here as well, but this time for k plus 1 terminal. For this right here, you start with k plus 1 times k plus 1 plus another one, which will be k plus 2, and then divided by 2. So we're trying to show k plus 1 factorial is greater than this thing here. Now have a look. We have the k plus 1 right here already. So if we can somehow show that this thing, of course this is not going to be exactly the same as k plus 2. But if we can show that this thing is greater than k plus 2, and the inequality still works, then we'll be done. So let's go ahead and make that happen. So this is what I'm going to do. I'm going to continue right here and do some algebra. So we still have the k plus 1, and I'm going to distribute the k. So we have k squared plus k over 2. Now, I want to show that this right here is greater than k plus 2. So first, I'm just going to use this right here, because we know k is greater than 4. So that's quite nice. I'm going to say, since k is greater than 4, not only I can replace this with 4, but I can also say, I'll just say we also know k squared has to be greater than k. And in fact, this is true when k is greater than 1, for sure. But since k is greater than 4, which is of course greater than 1, so of course this right here is true. So check this out. This is going to be greater than, this stays the same. K squared, I will use this right here, which I will just replace that with k. And then the k is greater than 4. I'm just going to say 4 right here, and over 2. Of course, right here we have k plus 4. That's of course bigger than k plus 2. So once again, I will say that's greater than k plus 1 times k plus 2 over 2. That is exactly k plus 1 terminal. Yeah. So as you can see, we have shown that k plus 1 factorial is indeed greater than this. So by mathematical induction, we are done with the claim. That means we can come back here and say that we only have two answers. n is equal to 1 and n is equal to 3, and that's it. It's not possible to find any other positive whole numbers after 3 because this will always be bigger than that. So yeah, that's it. I just realized that I want to erase the 24 and then the 10, otherwise it looks like 4 to the 24th power and 10 to the 4 to the 10th power. But I also forgot this right here. I should have put down IH because of the inductive hypothesis.